I've got this funny feeling that I just gave the same lesson 5 times. So maybe it's time to come up with a name for the common concepts in all of those lessons. And, well, that name is real vector spaces. So let's organize the concepts from the last 5 lessons and into a list and talk about what real vector spaces are in general. So a real vector space, V, is a set of elements called vectors they're called vectors even if they don't look like lists of real numbers. Which have addition and scalar multiplication which satisfy the, let's say, 6 familiar properties of addition and multiplication in the real numbers. First of all, for vectors u and little v, that is for elements u and v in the vector space capital V, we can add them in either order and get the same thing. Second, if we have 3 vectors, u, v, and w, then we can add them with parentheses anywhere we want and get the same thing. So we really don't need parentheses. Third, for every vector, the scalar multiplication by 1 does nothing. So 1 times v is v. If we have real numbers a and b, and any element of the vector space, any vector, then if we want to act by scalar multiplication on v by a and b, we could multiply ab first, or we could multiply by b first and then a later, and we would get the same thing. That's just what we'd expect from multiplication by real numbers, because real multiplication works that way. And finally, we have distributive laws. So for a and b in the real numbers and any vector, a plus b acting by scalar multiplication on the vector is the same as a on the vector plus b on the vector. And finally, if we have 1 scalar and 2 vectors, we have a similar distributive property. The scalar multiplication of a on u plus v is the same as au plus av. So we satisfy these sort of expected properties of addition and multiplication in the real numbers, and 4 more important properties. So since these properties are things that we almost take for granted without thinking about them, the next properties are different. I'm going to give them different numbers. I'll give them Roman numbers. So Roman number I is going to be closure under addition. And that means that if we have u and v vectors, then u plus v has to be a vector also. So when you add two of these together, you have to get something that's in the set. Two, if we have a scalar a and a vector v, then the scalar product of a times v has to be a vector. Three, we have to have a zero vector in the space with 0 plus any vector equals itself. So this is supposed to be a capital V, a 0 in the vector space with 0 plus any vector equals itself. And 4, for any vector little v and big V, we have to have a negative v in big V so that we can add that to little v and get 0. So that's also called having additive inverses. And number 2 is closure of scalar multiplication. So let's look at the examples that came up in the first 5 lessons and see that they really do have these properties. Maybe I should mention for the 6 sort of obvious properties, if the elements of the vector space, if the vectors are named by sequences of real numbers, let's say A1 through AN, with addition A1 through AN plus B1 through Bn equals A1 plus B1. So if we just add the corresponding numbers, and scalar multiplication, k times A1 through AN equals KA1 through KAN, then the first 6 properties will be satisfied. Now that's going to be almost all the time, which is why I don't want to dwell too much on the first 6 properties. Because whenever you're adding corresponding components and multiplying all components by a scalar, those first 6 properties just follow from the fact that you're working with real numbers and addition and multiplication. But the next 4 properties, the important ones, might or might not be satisfied depending on what the set is. So the examples we looked at so far were R2. R2 is the set of all ordered pairs AB, where A and B are real numbers. Now if we add 2 of those, we get another pair of real numbers. If we multiply one of those by a single real number, then we still get real number, real number. We have a 0 element because 0, 0 is an element of the vector space. And for every element in there we have its negative, because if a and b are real numbers, then negative a and negative b are real numbers also. Another example we looked at are polynomials in X with real coefficients. So certainly if we add two polynomials together, we get another polynomial. And if the coefficients of both of them are real, then the coefficients in the sum are real. If we have a single polynomial with real coefficients and we multiply by a real number, then we get coefficients that are real. We have a 0 element in there because 0 is a polynomial. We can add it to any other polynomial and get that other polynomial back. And for any polynomial, we have its opposite because we can just take all the coefficients and multiply them by -1. And then that is a polynomial that we can add to our original one to get 0. So a0 plus a1x plus a2x squared, etc., plus -a0 minus a1x minus a2x squared, etc., is equal to 0. 0 plus 0x plus 0x squared, etc. So multiplying all the real coefficients by -1 gives us all real coefficients still. So that's a vector space. We looked at matrices, real 2 by 3 matrices. So if we add two of those together, we get another real 2 by 3 matrix. If we multiply a 2 by 3 matrix by a scalar, we get another real 2 by 3 matrix. We have a 0 element because this is a real 2 by 3 matrix, and we add it to anything, nothing happens. And we have additive inverses because if we take a real 2 by 3 matrix and we multiply all the entries by -1, then that's still a real 2 by 3 matrix. And we can add, if we have a, b, c, d, e, f, and add it to -a, -b, -c, -d, -e, -f, then we get 0, 0, 0, 0, 0, 0. So real 2 by 3 matrices form a vector space, a real vector space. So what else did we have? We had Rn. So Rn is lists of n real numbers. Of course, if we add any two lists of real numbers together, we get a list of real numbers. If we multiply one by a real scalar, we get a list of real numbers. The 0 list is a list of real numbers. And for any list of real numbers, we can multiply all those real numbers by -1 to get the additive inverse. And then finally, we had a set which I'll write as r sine x plus r cosine x. By that I mean real multiple of sine plus real multiple of cosine. So that's the set of all functions of the form a sine x plus b cosine x, where a and b are real numbers. So if we add two of these together, we get another one, because the coefficients of sine are going to be real plus real, the coefficients of cosine will be real plus real, therefore they're both real. If we multiply one of these by a real number, then we still get real sine plus real number cosine. We have a 0 element because we could have 0 sine plus 0 cosine. And we have opposites because for a sine x, b cosine x, we could take -a sine x, -b cosine x. And if A and B were real numbers, then negative A and negative B are also real numbers. So that's a vector space also. In fact, that one is just like R2, really, because the A sine x plus B cosine x is really just A comma B. Addition and scalar multiplication are just like they are for A and B in R2. A sine x, B cosine x could very compactly be represented by A comma B as far as addition goes and as far as scalar multiplication goes. All right, now let's look at some more examples and maybe some non-examples. Let's look at 2 by 2 real matrices with zeros on the diagonal. So things like 0 square root of 2, negative 1, 0, and 0, 6, pi, 0. So if we add two of them together, we certainly get another one because the diagonal entries are going to be 0 plus 0, 0 plus 0. No matter what's off the diagonal, we're guaranteed to get zeros on the diagonal, so they're closed under addition. If we multiply by a scalar, no matter what the scalar is, on the diagonal we're still going to have zeros because scalar times 0 and scalar times 0 are both 0. So anything could happen off the diagonal, but we definitely are going to have zeros on the diagonal. So that's closed under scalar multiplication. Do we have a 0 element? Well, of course we do. Zeros on the diagonal and zeros off the diagonal too. If we add that to anything, we just get anything. Do we have negatives? Well, if we change the signs of all the entries except for the diagonal, well, even on the diagonal, because plus 0 is the same as negative 0. So if we change the signs, then we've got another matrix so that we can add our original matrix to it and get 0, 0, 0, 0. So we do have additive inverses. So that was a vector space. Now let's look at 2 by 2 matrices with no 0 entries. Is that closed under addition? That's not going to be closed under addition. Because suppose we have 6 pi negative 1 square root of 2. That has no zeros in it. But then negative 6, 1, 1, 1 is going to add up to 0, pi plus 1, 0, square root of 2 plus 1. So it's possible to add two of these together and get something that's not in this set. So therefore this is not closed under addition. And since it's not closed under addition, it's not a vector space. We don't even need to check all of the other rules. Let's try another one. Let's look at polynomials with only even powers of x. So that include constant terms. It'll include 0, 1, any constant, 1 plus x squared, not things like 1 plus x squared, because we're going to disallow we're going to disallow odd powers. I guess in general we're going to have things like a naught plus a2x squared plus a to the fourth x to the fourth, etc. Only non-zero coefficients next to the even powers of x. So if we add two of those together, I guess we'll only get even powers of x, because we're going to always add the coefficients next to the same powers of x. So we're not going to introduce any odd powers by adding these together. If we multiply by a scalar, that's not going to change the powers of x. It'll just change the coefficients by the scalar, but we'll still have only even powers of x. We have a 0 element because that's 0 x to the 0th. So, well, and obviously there's no odd powers of x in it. And do we have negatives of the elements? For additive inverses, sure. So whatever our coefficients next to the even powers are, we just take their opposites, and we still have only even powers of x. So that is another example of a vector space. Let's look at another example. Let's let r sub greater than or equal to 0 be all the non-negative real numbers. So all the real numbers which are greater than or equal to 0. If we add two of those together, then we get another non-negative real number. You can't add two positive things together and get a negative. Scalar multiplication. Scalar multiplication is going to be a problem, because what if we multiply by the scalar -1? Then we get a negative real number, which is not in our set of non-negative real numbers. So even though we have a 0, we don't have negatives. And actually, not having negatives is going to be a problem for additive inverses, because we want to be able to subtract anything that we added. We can't do that if all of our numbers are non-negative. So this is not a vector space. Let's look at Z3. So that's all of the vectors A, B, C, where each of these is an integer. So integers are all the counting numbers and the negative counting numbers. No fractions, no irrational numbers, no decimals. Alright, what happens if we add two of those together? If we add two integer vectors together, we get another integer vector, because integer plus integer is always an integer. If we multiply one by a real scalar, oh, then we're in trouble. Because if we take pi times 6, 1, negative 2, then we get 6 pi, pi, negative 2 pi. And those are not integers, not a single one of them. So this is not closed under scalar multiplication. So even though it has 0, 0, 0, and even though it has the opposite of anything that's in there, if 6, 1, negative 2 is in there, then negative 6, negative 1, 2 is in there. Those are all integers. This is going to fail to be a vector space, fail to be a real vector space, because it's not closed under real scalar multiplication. If there were such thing as an integer vector space where the scalars were all integers, then this would succeed. But that unfortunately is not called a vector space. That's called a Z-module, and if you take enough math classes, you might eventually get to Z-modules. But we're not going to use those in linear algebra. We're going to assume our scalars are real, and sometimes we'll let them be complex numbers, but not just integers. Speaking of complex numbers, let's try the complex numbers. So the complex numbers are all the numbers of the form a plus bi, where a and b are real, and I squared is equal to -1. But since we're not going to multiply vectors by each other, it doesn't really matter what happens if we multiply I by I. So if we have a plus bi and some other c plus di and we add them together, then we got another good complex number. So a plus bi plus c plus di equals real part a plus c, imaginary part b plus d. So that's still real number plus real number. If we multiply by a scalar, then we've got ka plus kbi, so that's still real plus real I, so that's still a complex number. We have a 0, of course we have a 0 element, that's 0 plus 0i, counts as complex. And if we have a plus bi, a and b are both real numbers, then we could take negative a minus bi. That's its opposite in the sense that if we add these together, we get 0 plus 0i. So we do have additive inverses, so that means that the complex numbers do form a real vector space. And actually, when we add complex numbers together, that is a lot like adding pairs of real numbers. AB plus CD gives us A plus C, comma B plus D. So the real part and the imaginary part are really just two holding places, just like first position, second position in R2. So the complex numbers, if we're just adding, work a lot like R2. So complex numbers with addition and scalar multiplication behave like R2. Real scalar multiplication, that is. All right, that's enough examples for now. The end.